as he said, so I'm here to talk about some OtterTune project we've been working on for a while. So this is something that we've been working on at the university at Carnegie Mellon that we have spun off in the last year as a startup. So I want to spend some time talking about the things that we've learned of taking, a sort of state-of-the-art machine learning project in the university and having it run in the real world. And what are some lessons we've learned from that process? So I'm going to begin by talking about the background information about what problem OtterTune is trying to solve and why we think machine learning is the right approach to this. And then I'll talk about how OtterTune actually works. And then I'll spend some time talking about 2 deployments we've had in the real world, and again, some things that we learned from that. And the main takeaway actually is going to be, not to disappoint anyone, is that the machine learning stuff actually is not the highest priority when you're trying to do automated database tuning. We find that all the interactions with the database system and understanding what the database system is actually trying to do turns out to be the most important part. What machine learning algorithm, what machine learning framework you end up using, less so. And then I'll just finish up talking about what we're working on next if we have time. All right, so let's get right into this. And I think the way they're doing this is that if you have questions, post them in chat, and we can answer them at the end as follow-ups. All right, so OtterTune is focused on knob configuration tuning. So by knob, I mean a runtime parameter that the database system exposes to you, you as the human or the administrator, that allows you to control the behavior of the database system. So we call them knobs. That's sort of a catch-all phrase. MySQL calls them system variables. I think Postgres calls them settings. Right? They're all the same thing. It's something that you can set to control how the database system is going to do certain operations at runtime. So think of buffer pool sizes, caching policies, log file sizes, right? Enabling different features in the system. They all have these knobs, and they all can affect the performance of the database system quite a lot. The reason why these knobs exist is that as the developer was building the database system, at some point they had to make a decision, how much memory should I allocate for this hash table? And then rather than putting a pound define in the code and assuming that would be good enough for everyone, they instead kick the can down the road and expose it as a knob because they assume that someone else is going to come along who knows how the application wants to use the database system, knows what data you're trying to store, knows what queries you're trying to execute, and therefore will be in a better position to be able to set that knob correctly for that, for your application. Because if you can set it correctly, then you can get the best performance out of the database system. But of course, now the problem is that over the years, people have been adding, dozens and hundreds of these knobs, and the challenge of actually trying to tune these things for every individual application exceeds the sort of mental capacity of even human experts, right? And every year, new releases come out. Postgres 14 is about to come out pretty soon. They're going to have a bunch of new knobs. So just to give you an idea how bad this problem is, my PhD student did a survey where she just looked at the last 20-year release history of the 2 most popular open source databases, MySQL and Postgres. And every new release, she just went and counted in the documentation how many knobs they expose. So at the beginning of the century, MySQL and Postgres each had less than 100 knobs. But then over a 20-year period, MySQL grew by 7x and Postgres grew by 5x. So again, there's a lot of knobs, and to set all these correctly is a difficult problem. Now, admittedly, for MySQL's 600 knobs, not all of them will affect performance, right? Same with Postgres. A bunch of them will be like file paths, directory names, port numbers, right? Things that you wouldn't want a machine learning algorithm or some kind of optimization tool to try to figure out how to set, because if you don't set the port number correctly, then the system doesn't work. So, but there's still enough of them, probably in the several dozen for every database system. Commercial guys have a bit more that you actually want to tune that will affect performance. So if I'm saying that the challenge of setting these knobs is super important, it can really affect the performance of your database system and its efficiency, then how are people setting these knobs today? Well, there's sort of basic 4 approaches. So one is you just DIY it, do it yourself. And typically we found when we talk to companies is that there isn't a full-time DBA anymore. It's sort of been pushed off into this, falls under this DevOps umbrella. And so that typically means is whoever set up MySQL or Postgres or whatever database using at the last job, they draw the short straw, and they're responsible for setting up the database at the new job. But they're not an expert. They're not a full-time DBA. They're just a developer. So what do they end up doing? They just Google MySQL tuning, Postgres tuning, Oracle tuning, whatever, and you're going to find a bunch of these blog articles where they recommend maybe the 5 or 6 knobs that you may want to tune to improve performance. But it's trial and error. What they're describing here oftentimes isn't the best thing to do. We have found actually in some cases where what these blogs actually recommend are actually the exact opposite that you want to do for certain applications. Right? These are sort of general, good guidelines. But again, the DevOps person is just winging it. They don't really know what's going on because they don't fully understand what the database system is doing. All right, so say you don't want to DIY it. Say you want to actually be a bit more responsible, or you have a little money, you can try to hire an expert to come do this. So you can hire DBA, again, someone who is intimately familiar with the internals of the database system and maybe knows something about knob tuning. We have found actually the DBAs that we talk to that do some knob configuration tuning, they typically have, again, just maybe 5 knobs that they're comfortable with tuning that worked well for them in the past, and they try to apply that again. But the problem is this is not cheap and this is not scalable. So this is from the U.S. government, the Bureau of Labor and Statistics, from May 2019, and they have that the average salary of a DBA in the U.S. is around $96,000 a year. Again, that's the average. Certainly, if you're on the East Coast and the West Coast, DBAs are easily going to cost into the 6 figures. All right, so this is just, again, $100,000 just for one human to come, tune your database system. And DBAs are doing a bunch of other things too, right? They're doing disaster plans, they're doing query tuning, index tuning, right? Knob tuning is usually relegated to a low priority just because it's so challenging and time consuming. They have a bunch of other stuff that they need to do. So just because you hire someone for, $100,000 doesn't mean they're going to come be able to tune your database immediately. And certainly if you have a fleet of hundreds, even thousands of databases, you can't hire enough humans to come and tune each database for the application that's running on it. So the next approach is to use these automated rule-based tools. So all the commercial vendors, Oracle, IBM, and SQL Server, Microsoft, they have their own proprietary tools. There's PGTune for Postgres and MySQL Tuner for MySQL. And these all work basically the same way. They have a bunch of hard-coded heuristics written by the database developers themselves that just use, sort of conventional wisdom of how to tune things. Like for MySQL, you want to use 75% of the memory on the box for the buffer pool. Right? So they're just codifying that information. So you punch in how much CPU you have, how much memory you have, maybe what workload you're using, and then they'll spit out some basic recommendations for a small number of knobs. But we have found in the cases, when we compare against these guys, they're not optimal either, and we can beat them. So what I'm arguing for tonight or today is I think the better approach is to use machine learning, rely on the modern sort of machine learning and artificial intelligence tools that have come out in the last decade, and leverage that for tuning these configuration knobs in databases. And we think that this is going to yield to better results because you can uncover things in different implicit dependencies between these knobs that a human's not going to be able to discover. And over time, as new features get added to the database systems, it's just a matter of retraining the models with these new features and not worry about these guys ever coming and updating their code. Right? We can just learn automatically over time. So this is what OtterTune is. So OtterTune is a machine learning-based database configuration tuning service. So the idea is that we're going to train machine learning models that know how to optimize the knob configurations for different database systems in order to improve performance or improve the efficiency of the database system. And the ultimate goal is either you want to get, I want my queries to run faster, I want to run more transactions, have lower latency, or I want to actually maybe downsize my my hardware installation or my hardware specification that I'm using for my database so I can run more efficiently. Because we're all paying Jeff Bezos way too much money on AWS. So if you're over provisioning your database on Amazon, OtterTune can come and help and dial that back. So as I said in the beginning, this is a startup that we've spun out of the university. This is something we've been working on for 6 or 7 years now, and we've gone through a bunch of vetting in the academic space. And now we're actually trying to apply this and make it work in the real world, because we found that it actually did work when we used the research version. And so we're interested in seeing what happens when we try to run it at a larger scale. So there's several papers that describe the key algorithms of OtterTune that are publicly available that you can go check out. So right now, the commercial version of OtterTune supports Postgres and MySQL, all versions except for MySQL 5.5, but that's old. And then we're currently targeting Amazon, and we can either run for RDS or for Aurora. We have done deployments of OtterTune running on-prem. We haven't really been asked to run in other cloud settings like GCP or Microsoft or IBM. Right? Amazon is again, Jeff Bezos is the world's richest man for a reason, the world's richest person for a reason. A lot of the databases are running in this environment. So it's always risky to do this while giving a live talk, but I'm going to give a demonstration of OtterTune. And so what we're going to do here is we're going to deploy Amazon, or we're going to deploy a Postgres database instance on using Amazon RDS. So RDS is their hosted database as a service, but it's the stock version of Postgres. It's not Aurora, where they've ripped out a bunch of the internals. And we're going to run the industry standard TPCC benchmark using our benchmarking framework, where we're just going to run transactions and try to measure how fast we can, how fast we can push this system. What we're going to do is we're going to set up the database twice. We're going to have one database where we're running TPCC, but we're not going to do any tuning. We're going to call this the monitoring database, or the control database. And that's going to use the default configuration that Amazon gives you when you first set up your database. And then the second one will be one where we're going to let AutoTune actually go ahead and try to optimize configuration to improve performance. And we'll use the monitoring one as a baseline to see, are we making things better as we tune the system. So I need to replicate my screen here, which I think is going to break. Yeah, so I come back to this, share screen again. Right, I think you guys should be able to see that. All right, right, so this is the AutoTune dashboard. So we're going to go ahead and create a new database. And we're just going to plunk in a bunch of quick information. So we're going to run on Amazon. We're going to run Postgres. We put in an identifier. And we have to select a region. So we're on East 2, right? Our database name, we'll call it TuningDB. We have to tell OtterTune what database we want to connect to. And then I'm not going to show this part, but we've already set up a bunch of AIM permissions in Amazon that gives OtterTune access to the database. So this stage, what's happening is OtterTune is connecting to AWS, making sure that I actually can connect to the database and has the proper permissions to go retrieve configuration parameter groups and CloudWatch information, because we're going to use that to figure out what's happening. So at this next stage, we can specify whether we want to do tuning in the database, which actually try to optimize configuration, or just do monitoring. So because we want to actually optimize the database, we'll keep it at monitoring. And then we will, there's a tuning schedule, so if we ignore all that for now. But then here, OtterTune has already recommended a bunch of knobs that it wants to optimize. So we'll go ahead and let it choose the ones that it thinks is the best. So I'm not gonna talk about this here, but there's a whole separate algorithm we use to figure out what knobs we think will have the most impact on performance. And this is initially starts off based on all the global data we've collected from tuning databases. So now we're gonna go down here and put in our password information. So this is now going to allow OtterTune to connect to the database system itself. I'll talk about what permissions are actually we're using, but it's basically just to be able to go read the metrics or the internal statistics that the database system generates. I'll explain what that is as we go further along. But the key thing about OtterTune is that we actually don't need to see the queries. We don't need to see any user data, right? Because the metrics we're going to collect from the database system, pages read, pages written, so forth, that is representative enough of what the application's queries are on the database, or what you're actually trying to do in the database. So we don't need to see the queries like in Vivid Cortex. We don't need to see actually any of the user data, because we're just tuning the knobs. And there's the basic information is to read whatever Postgres is generating or MySQL generates for InnoDB stats is enough for us to figure out what's going on. So now with everything sort of set up, we can go just come here. You see if OtterTune's connected to the database, it's gotten the first configuration. And we can see that we have some basic information about it. So we're going to let this go for a bit. Let's continue with the talk, and then we'll check on it at the end and see how OtterTune compares against the baseline. So now, again, this will break if I do extend. It broke PowerPoint. Okay, so let's try that. If I got this. See all slides, and then let me share screen. Okay, I think we're back in business, right? Okay. So, all right, so how does Autotune work? So as you saw, we have our target database that we want to tune, right? It can be an RDS, it can be on-prem, but you provide us with some basic credential information to be able to access the database system. We then store that in our, we store that in our service, and then there's a driver running in Kubernetes that it runs in our data center or in our environment or your environment that connect to the target database and retrieve these runtime metrics, pages read, pages written, locks held, and so forth, and the current configuration. The driver then stores that in OtterTune, the internal repository, where we keep track of all the databases that we've tuned before, and then we feed that into our compute engine that then trains statistical models that can predict how the database system's behavior or performance will change as we start changing the values to the knobs that we want to tune. So you tell us that we want to optimize for throughput, we want to optimize for latency, and so we'll train models to say, if I start tweaking the knobs a certain way, what happens to that objective function? And then we do a gradient descent on these models to then find a new configuration that we think will improve performance. We send that back over to the driver, who then applies it, and then we repeat the process. We just, we apply the change, wait a little bit, observe what happens, and then we come back around and see what happens. So, sorry, it's running on. It's using the timer thing. Always fun. All right, sorry. That's why it was auto transitioning. Okay, the worst default feature in PowerPoint. Okay, so I've already pointed out the one key advantage or sort of ideal characteristic of Autotune is that the driver doesn't need to see any user data and doesn't need to see any of the queries. So there's less of a security concern, right? We're not looking at sort of the most important aspects of your business. We're only looking at these metrics. And we've done deployments in Europe, and there's security people at these major companies have looked at what we're trying to do and felt that there wasn't any GDPR violations. The other important thing aspect about this is that this feedback loop is continuous, meaning that we apply configurations that then we use them, to bolster our models to help improve the accuracy of our choices for new configurations. And at some point, the compute engine recognizes that that the models have converged for your current workload situation, that we think we have the best configuration for your database right now, and then it'll turn off tuning and to switch to a monitoring mode, and uses that to observe whether has the workload changed since we last did tuning, and if so, then it can re-enable tuning to make changes based on how the workload is shifted. So like if you put out a new release of your application, you have a bunch of queries you've never seen before that changes the workload pattern, OtterTune can recognize that and kick off the tuning process again. Okay. So I want to show two quick benchmarks we've done running on Amazon RDS. So the first one here is Postgres. We're running TPCC again, and this one here we're gonna deploy the database, the Postgres database on 2 instance types. So the first one will be a DB M5 4x large. This is with 16 CPUs and 64 gigs of RAM. We're also going to give it 4,000 provision IOPS, and then we're going to have a smaller database where it has fewer CPUs and less RAM, and it has half the amount of provision IOPS. So the first main takeaway here is that, well, we're comparing against the RDS defaults. That's what Amazon gives you when you create the instance. A surprising number of people still run with the RDS default. Like they think Amazon has tuned the config for them that's going to be really good. And that's true. Amazon has tuned the configuration for the RDS deployment. It's better than like the default config you get when you do apt-get install to install Postgres on Linux or your local box. Those configs are always terrible. They assume you're running on a machine with like 160 megabytes of RAM. So Amazon has done a little bit better, but it's still terrible. PGTune is one of those rule-based tuners that I mentioned before, where you punch in your number of CPUs, the amount of RAM, and maybe what your workload type looks like, and it comes back with some basic recommendations. And then we have AutoTune is using machine learning. And so you see here that we can get over double the performance of what Amazon's going to give you by the default, just in a short amount of time. And then same down here on the smaller box, we still get double the performance of what Amazon gets you by default. We still beat PGTune. But the key takeaway here for this graph is we're actually getting better performance on the smaller box than what Amazon gives you initially with the default configuration on the larger box. So this machine here will cost you $17,000 a year. This machine is half the price. So you're getting the same performance on that you're getting, you could get on this more expensive machine, but at half the cost. So this is why I'm very bullish on the idea of using machine learning. Like, we didn't have to be an expert in Postgres to figure this out. The machine learning stuff figured it out for us. You run the same experiment now on MySQL. The machine is the same. The two instance types are the same, except we're now doing 2,000 provision IOPS versus 1,000 provision IOPS. And so ignore whether Postgres is faster than MySQL. Like, that doesn't matter. It's really, again, that we see when we compare Autotune against the Amazon default config. In this case here, we're getting we're getting almost getting 4x faster, and then on the smaller box, we're getting I think almost 5x faster. And so the MySQL tuner is actually a little bit more sophisticated than the PG tuner one. But the MySQL tuner actually watches the InnoDB statistics for a little bit and then makes recommendations. But in our case, because we were starting with the Amazon default config, Amazon already tweaked a bunch of the knobs that the MySQL tuner set, but we can still outperform them. And again, once again, we're getting actually better performance on the smaller, cheaper machine than you would get in the larger, more expensive machine. All right, so this machine here is going to cost you $14,000 a year, and this machine is going to cost you $7,000. So these, we ran these kind of experiments again when we were at the university. We thought this is, this is amazing. This is, this is definitely something that would help in the database world. We wrote our first paper in 2017 about OtterTune. We published it in SIGMOD, which is the big academic database conference. But when it came out, like, nobody really paid attention to it. I mean, the other academics and the researchers saw it and like, oh, that seems like a good idea. But nobody in industry really paid attention to it. But then through total luck, I just happened to meet the guy that runs all of Amazon's machine learning division. He came to Carnegie Mellon. I got 5 minutes of his time just to thank him for giving my PhD student a couple $1,000 to run her experiments on EC2 and RDS. And he was like, great, can you write a blog article for us? Because the Amazon just started a new Amazon AI blog and they needed articles. And so we did that. We converted our Sigma paper into a blog article for them. And when this came out, this is when everyone started emailing us and saying, we have this exact problem. We want to pay you money to fly a student out to come set up OtterTune for us. And so we got a lot of crazy emails. People talking about, like, we're going to make a lot of money with this, how we're going to take over the world. This guy kept emailing me nonstop and, saying all sorts of crazy things. And so unfortunately, my PhD student didn't realize that these people were crazy and did not know, like, hey, don't respond to them, because that made things worse. But after all of this nonsense, we actually got a really interesting email from somebody in Paris who said that they were in charge of the database performance and engineering team at this major bank, and they were actually looking at using OtterTune for their giant database fleet. So this turned out to be one of the first deployments that we did of OtterTune outside the real world, because it's fun to make TPCC run faster, but we really wanted to see whether this would our approach would stand up to real world workloads. So Societe Generale is a major French bank, and they told us that they had a fleet of 1,000 Postgres databases running in their data center in Paris, and it was a self-provisioning sort of internal architecture where somebody in IT could go into a website and say, I want a new Postgres database in an online form, and then it would automatically spin up the instance for them. And so they would specify, like, what the workload was going to be. And so there was some basic tuning that was being done, based on whether you select OLTP or OLAP versus HTAP. But beyond that, they had not done any sort of fine-grained tuning on each individual instance. So they told us had 1,000 Postgres databases. We collaborated with them remotely. They took on our French master student as an intern. to sit on site and get OtterTune up and running inside their data center. And then once we got it working, they went to go now look at the 1,000 databases that they wanted to go tune. And then they came back to us and told us that the real number of Postgres databases that they had to tune was 1. Because what happened was the bank had this big initiative a few years prior to this, where they told everyone at the company, hey, we need to start using more open source software. So then the word got around the bank at all the managers that for every new project and the budget justification, if you just in the checkbox where you said what open source software you were going to use, you could just click Postgres. It would spin up a Postgres instance. You never put any data in it. You never ran any queries on it. You just used Oracle and paid Oracle like they normally would. And then none of the bean counters ever checked and ever cared. So they literally had 1,000 Postgres databases that were completely idle running in their data center. So this was a bust. And so then they came back to us and said, okay, yeah, we're primarily an Oracle shop. Can you port OtterTune to make it work on Oracle? And so we had a master student on our side at Carnegie Mellon port OtterTune to make it work on Oracle. And this is an important part, as I said in the beginning, it's the machine learning part doesn't change because the machine learning algorithms don't know what they're optimizing. It's just numbers. They don't know whether it's Oracle, they don't know whether it's Postgres, right? It's all the infrastructure they talked about in the driver and how that interacts with the database. That's sort of the hard part. So the student was able to get OtterTune to work on Oracle in a few months' time, but the challenge wasn't, again, making changes to the machine learning algorithms. It was making our drivers speak to Oracle, know how to work, Oracle stores configs, dealing with failures and so forth. So once we got this working, the bank gave us then access to a 1 terabyte database that had been running in production. It was a read-heavy old tweak workload. It was basically their internal version of Jira. What was interesting about it is because that the bank has like 100,000 employees all around the world. So at any time during the week, the work week, somebody's using this this internal website for ticket tracking, and so it had a lot of traffic. And this database had already been tuned by their in-house experts, and they weren't really able to make a dent in it and sort of making big changes in improving performance. So the thing they wanted us to optimize was this thing called Oracle DB time. So in my examples with TPCC, we were trying to optimize for throughput. DB time is a proprietary Oracle metric. It's basically a summation or combination of a bunch of different latencies inside the system. So again, we didn't have to make any changes to our machine learning algorithms to support this. We just had to change, tell it, hey, here's the metric we want you to optimize. So the deployment went like this. So we had our driver that was running in their data center, along with the Oracle database running their data center. So in the very first step, what we would do is just start the database and then immediately check the logs to see whether the database came up correctly. So this turned out to be a recurring problem with Oracle, where if you set the knobs incorrectly, or a series of knobs incorrectly, a set of knobs incorrectly, Oracle would freak out and say, I don't want to start. And so we had to go check the logs and see whether it crashed because of something we did in the configuration or something else going along in the system. I should also say too, this is running on spare hardware. So they took a snapshot of a production database, captured a workload trace for 2 hours of the queries that the database was executing, and then they spun up a bunch of VMs that were running the same data center on the same hardware as the production database. And so we're running all our tests and all our experiments on replicas and not the production database. So the next step would be to clickers. Reload the database from the snapshot, and that puts the database back into the state it was in at the moment we took the snapshot after replaying the workload. So this ensures that every single time we try a new configuration, we'll always have the same starting point for the database. So we know that if we see the performance get better or worse, it's because of something we're doing in the configuration, or at least we hope it is, and not some change in the workload, because the workload is always going to be the same. And I will say that Oracle had really good tools to create snapshots and do workload replays, on the system, much better than any of the open source things I've seen for Postgres and MySQL. All right, so then the next step was we actually ran an IO micro benchmark to measure the disk read and write speed for the database system. And we had to do this because the database was running on a shared disk architecture, because for security reasons, no database was allowed to write to local storage. They always had to write to a shared NAS on the network for auditing and regulatory purposes. But the challenge was because this was a shared disk, other things were reading and writing to it at the same time, and we'd see wild oscillations in performance. So before we ran every new configuration benchmark or every new configuration, we would run FIO and measure what the performance was on the disk. Right. So here you can see the result of this. So the red line is the measurements of running the micro benchmark on the shared disk, and then the blue line is the micro benchmark running on a local disk. You see here there's a huge blip in performance where the disk speed got 5x or 3x slower than what or 2x slower than what it normally should be. And this is nothing to do with what we were doing in configuration tuning with AutoTune. Just had to do with something else was going on the network, and of course we don't know what it is because it's running in their data center. And so the challenge with this was, how do we now, how do the machine learning algorithms figure out, oh, I'm seeing a spike in my performance got worse because performance got worse during this for this new configuration. Is that because of something I tuned, or is it because of something happened in the environment? So we tried a bunch of tricks to try to normalize this, performance results from the database system based on what read speed we see in these micro benchmarks. And at the end of the day, it didn't actually make a difference. It just collecting more data smoothed this out and it made this go away because most of these blips were transient. All right, so now that we're going to collect metrics from the database system, and again, these are just all the internal performance counters that every single database system maintains. And then we rerun our workload trace. And then we collect the metrics again, compute the delta between the before and after the workload. So this is like data read. You know what it is here, you know what it is after, you subtract that, and that tells you how much data you read when you're in the workload. And then we ship this over to our Autotune service, along with the current configuration. And then we crunch on it, as we talked about before. And then Autotune will then generate a new configuration that we send back over to the database system, to the driver, that then applies it to the database and repeat the process over and over again. So I'm going to show one graph here of the overall benefit we were able to get for this database. And this is published in a BLDB paper we had come out this year, working with our partners at the bank, that describes the whole process of getting this deployment set up. So over here on this side of the graph, this is the configuration. Using the configuration that was tuned by their human experts. And so this is the y-axis is this DBA time, so lower is better. And then over here, you see the best configuration that Autotune was able to generate. And so this iteration, this is how many times it sort of went around this loop, trying configuration, observing what happens, making tweaks to it, and then applying a new one. And so this is roughly a 3.5 day period. So this takes quite a bit of while because it takes a long time to reload the database and run the workload trace over and over again. So the main takeaway here is that we were able to reduce the resource consumption for this database around 50%, according to this DB time. So this is great because so now we go back to the bank and said, hey, look, we improved this database performance by 50%. How much money are you going to possibly save? And they had no idea because they were like, we've never been in a position to pay Oracle less money for our databases. So they were like, hey, this is good, but we just don't know. Back of the envelope calculation says that you probably turn off 2 CPU cores on this box. And Oracle charges, at least they say on the website, they charge about $50,000 per core. So it's roughly about $100,000 savings for this one database. And again, it's all funny money math. So take that with a grain of salt. All right, so what are some of the things we learned from this deployment? So I want to go through these quickly, and then we'll go through the next deployment. So the sort of most obvious thing here is that humans make mistakes. Human experts make mistakes. So part of the big benefit we were getting in OtterTune was because they told us that the DBAs had tuned this database, and that was sort of partially true because they had tuned it when it was an earlier version of Oracle 11. And then they did a massive upgrade across their entire fleet and bumped up to Oracle 12. And then nobody had time to go back and check, okay, should we look at these knobs again and try to retune them? And that's sort of what I'm arguing why you want an automated solution like OtterTune, is because the DBAs were doing a bunch of other things, for all the databases that they had to run. They have hundreds of all these giant Oracle databases, and no one had the time to look at every single one. And so my argument is that in this case here, this is a good example where an automated solution like OtterTune could observe the database system recognize that, oh, I've upgraded from Oracle 11 or Oracle 12, or even a minor version like 12.1 to 12.2, and therefore I should reevaluate whether I'm running with the right configuration. The next challenge we had to face was actually replaying that workload. That actually turned out to be really, really hard. And the challenge is because the time it takes to replay the workload is very much dependent on what the configuration was. So it was a 2-hour trace. We took a 20-minute slice of that trace. I mean, that's what we'd run in every single iteration. But the problem is, like, sometimes if you had a bad configuration, that 20-minute trace could end up taking hours, because it was just running so slow. And so the solution to this is sort of obvious, that you just say, okay, well, if I recognize that most of the time I can finish in 20 minutes, but now it's been 2x that or 3x that, I know that I'm not going to get any useful data out of this. I know that it's a bad configuration. So let me go ahead and just kill that configuration, that trial, send some feedback information to my models and say, this is a bad configuration, don't try it again. And then that way, you're spending less time on things that end up generating useless training data for you. All right, so this works, but then now the problem is, how do we also then give feedback to the models and say things go bad? And it isn't just because things ran slower. There's other situations where the configuration was just simply, cause the system to fail to start at all. And we need feedback on our models to say, don't try this again. So I've already started to talk about the first two scenarios. The slow one, again, 20-minute trace takes an hour. You go ahead and kill it prematurely. The next one is, again, the database fails to restart, because I'm not saying OtterTune would do this because we can set the balance, but like if you set a memory size to -1, the database recognizes that that's an invalid value and then fails to start. The more challenging one that was really nuanced is when the database system fails because of a bad configuration value, but it doesn't fail right away upon boot up, it fails at some other later period. And so I don't think we've seen this in Oracle. Sorry, I don't think we've seen this in Postgres and MySQL, but we've seen this definitely in Oracle, where there is some memory buffer knob you can set, but when the system booted up, it didn't actually try to allocate that memory right away. Like for the buffer pools, every database system allocates that memory right away. But this was like for some JVM buffer or something, and the system would boot up. It's an invalid knob, but because it didn't try to allocate the memory at that moment on boot up, it boots up just fine, and you start running queries on it. Then like 5-10 minutes later, it tries to allocate the memory for that, based on that knob. Then it freaks out and says, this is an invalid value, and it goes ahead and crashes, right? So like, how do you, again, is it something because of what we did, or is it something because of the environment? Figuring that out was actually super tricky. All right, so there's two problems with bad configurations. As I said, the first one is to try to identify when there's a failure. There's no magic to this. All we do is just scrape the logs and look for well-known error messages and exit status codes and things like that. So like Postgres here, if I set the buffer pool size to a negative value, Postgres catches that when you try to boot up and throws an error. So we just scrape the log for these kind of things and recognize that, okay, something bad happened. Same thing in the case of like the delayed failure, there's no magic to that. You just scrape the logs and say, okay, it seg faulted or it crashed because of some knob that got set. And Oracle actually does a pretty good job telling you what the knob was. Same with MySQL and Postgres. The more tricky thing, though, is how to then give feedback to our machine learning models and say that this is a bad configuration and don't try it again, right? So the first idea may be, okay, I'll just set the objective value, like the throughput and latency, to like negative infinity, because that's just like, that's the worst possible number you can have, and that's enough to say, don't do that. The problem is when you start doing like gradient descent, if you have like a huge step off in your solution curve from something that was sort of okay, and then it goes down to negative affinity, then that could prevent you from maybe finding the optimal value that might be close to that cliff. And so if you look in the machine learning literature, they say just set the return value, the objective function value for a bad configuration or a bad deployment to be the worst configuration you've seen so far. And that's enough to keep the search algorithm away from trying to pick that thing again. Sometimes the literature says 2x the worst or 3x the worst. In all our deployments, we haven't seen that make a difference. All right, so this was good. So this was, like I said, we published a paper in BLDB that proved that this worked. And this is sort of, but we still wanted to, look at more workloads and just sort of get a sense of make sure that we think OtterTune was, could be used in production environments. So the next deployment we did this year was at Booking.com. And so they actually reached out to us before the pandemic in early 2020. And, they have a large, MySQL fleet running in their data center in Amsterdam. And they want to see whether OtterTune can improve performance. They already had in-house MySQL experts that tune the database configurations. They want to see whether OtterTune can go beyond that. They had their own rule-based tuner that they wrote for their Puppet scripts. So like whenever they deployed a new database, the script would look at what the hardware specs were, how much CPU there was, how much RAM there was, and use the conventional wisdom formulas that everyone uses to set MySQL knobs for certain things, like the buffable size a certain way. But beyond that, like occasionally a human would come and tune each database individually, but nobody was sort of looking at the entire fleet. So again, they reached out to us before the pandemic. Then the pandemic hit, they disappeared. Then they came back in the summer, and they were looking at using OtterTune to help them do consolidation to reduce their server footprint. So for this, OtterTune is going to end up tuning 23 knobs in MySQL. And this is going to be a combination of dynamic knobs and static knobs. And so a dynamic knob it's the MySQL term for this, but every database has these. It's the knobs you can tune without requiring you to restart the database system before they take effect. Like, you can change in the Postgres, you can change the auto vacuum settings. It doesn't require you to restart the database before the database can pick up those changes. Then there's these static knobs that do require you restart the database before they take effect. The commercial systems have fewer of these knobs that require a restart. The open source guys are getting much better, but no system can completely be modified without restarting. And so for these guys, since they wanted to optimize reduce the server footprint, increase the efficiency of MySQL running in their boxes. They want us to keep the same P99 latency for the queries, but try to reduce the number of concurrent threads and CPU utilization that MySQL is using on the node. The other thing about this too is that they didn't have a staging database or staging environment like we had at the French bank, where we could run all our experiments and not touch the production database. They wanted us to actually tune the database while it was in production. And so because of this, because it was serving live queries, it was the internal backend services for Booking.com. So it wasn't like actually serving the website, it's all the internal things. But they had real internal customers using the database actively. That we would only tune the database, a 9 to 5 period during the work week when the DBA we were working with was on pager duty. And they only allowed us to restart the database once per day. In the bank's case, we could restart the database as much as we wanted because it was running on replicas that it didn't mess anything with the production database. Because this was live, we only could restart one time a day, and they want us to restart between 9 and 10 a.m. All right, so the way it worked is that we have a driver running in their data center, and then we're actually going to have the driver connect to 2 databases and collect metrics. So the first is going to be our tuning database, and this is where OtterTune is going to be actively making changes to the database's configuration. But because we don't have that workload trace we had at the French bank, we have no way of knowing whether the changes we're making are making things better or not, right? Because the workload isn't reproducible, these are read replicas. They're live queries coming in. We don't control what those queries are. So we would also connect to what we're calling the control database or monitoring database, similar to our experiment that we're showing here today, where we wouldn't do any configuration changes. We just observe what the metrics were on this system. Now, they're not running exactly the same queries because there was a load balancer in front of this where it would send query to one node. But over longer periods of time, they were essentially running the same workload because it was evenly passing the queries to each node. So we start off by collecting the metrics from both of these databases. And for this one, we would collect both a combination of InnoDB stats directly from the database system, but also a Telegraph endpoint that was collecting OS level stats on each node. So that's similar to what I'm showing here today with the SaaS version running in RDS. We can collect the CloudWatch and get additional metrics beyond what the database system is generating. All right, so then we collect our metrics, and then we just wait. Because again, we don't control the workload. We just let the application run queries on these nodes. for a certain period of time. And then when the time's up, we go back and collect metrics again, compute the delta as we did before, and then ship that information over to the OtterTune service, which then generates a new configuration that we then install on the tuning database. And if it was in the time period where we were allowed to do a restart, we would go ahead and restart the system. So we actually deployed it on 2 databases. It worked so well on the first database, they asked us to try it on another one. And so for this first one here, the main takeaway is that we didn't really have we didn't really reduce the latency of queries that much, which is good, which is fine, because that's not what they want us to do. But we were able to reduce the CPU utilization and the number of running threads in MySQL by over 20% for both of these cases. And so the back of the envelope calculation says that in a cluster with 20, 25 nodes, you're looking at maybe turn off 2 up to maybe 4 machines, because now every machine can essentially use the same hardware but do more work without affecting latency. For the second database here, we actually got a huge reduction in their P99 latency, almost 40%, but a more modest reduction in CPU utilization. This is because this particular cluster was actually underutilized quite a lot. So there wasn't enough queries being sent into it that OtterTune had enough had enough working room to actually try to improve performance. We definitely improved their latency, but not the utilization level that they wanted. And that's something outside of the machine learning algorithms that we can't control. All right, so let's talk about 2 things that we learned from this deployment. The first one was actually very surprising, is that sometimes there are external factors that are involved in how people tune their databases that are not readily apparent or visible to the machine learning algorithms. And so in particular, at Booking.com, they were setting the MySQL buffer pool size to be only 50% of the total amount of memory available to the node. So it was like each box had 128 gigs of RAM. They were only setting it to about 64 gigs. Again, the conventional wisdom of MySQL, if you read the documentation, says I think 75 to 80% of the total amount of memory on the machine should be allocated to the database system. So no surprising, OtterTune figured out that you should set it to be 96 gigs of RAM. And when we went and showed them this, we asked them why were they officially setting the memory so low, and they said because that they were concerned about flash mobs, or like an application flooding the cluster with a lot of queries all at once, and MySQL could run out of memory if it tried to create too many connections all at once. So they artificially set the buffer pool size low just in case at some point they have to deal with a huge flood of queries. It didn't happen that often, but it happened enough where they were concerned about it. But it was one of those things where the guy or whoever on their team who came up with that rule to set it to be 50% of memory that's on the box wasn't there anymore, and they didn't really, nobody really knew, whether that should still be the case in the newer versions of MySQL that they were using. So OtterTune just, doesn't know all these things, made the recommendation based purely on performance, but there are cases where you may want to set knobs a certain way, or not have OtterTune set knobs a certain way, based on sort of other things that humans know about, but the machine learning algorithms don't. And so the way we handle this is that in the OtterTune interface, you can specify the bounds for knobs, whether certain knobs can be set correct a certain way or not. The next challenge is how to deal with the restarts. Again, in the French bank deployment on Oracle, we could restart the database anytime we wanted, no big deal, because it wouldn't affect any human or any application. But in case of this deployment, it was running in production, so we need to be more careful. The other challenge we had to deal with is, even if we could restrict when the data system was allowed to restart, how long it was going to take to restart was sort of outside our control, because it depended on many different factors of the database system, the environment, and its previous and new configuration. So the example I always like to use is MySQL has this knob that controls the log file size, and depending on what the value used to be and what you set it to, that will determine how long it's going to take before the database comes back online after a restart. So if the knob is currently set to 5 gigs, you set it to 10 gigs, restart, MySQL comes back and says, well, I was 5 gigs, now I can go up to 10 gigs. So I don't need to do anything because I'm already within my limits. But if I go from 5 gigs to 1 gig, then MySQL comes back on restart and says, well, I need to compact my log file to get down to be under my 1 gig limit, and that can take up quite a bit of time depending on how fast your disk is and what else is going on in the system. So the way we would handle restarts in the service is that this is something that a human has to tell us. We now expose in the UI the ability to say when you want to allow to restart, how many times you're allowed to restart, and OtterTune can figure out as it generates new configurations with the machine learning algorithms whether it should pick knobs that require restart if it's not within this time window when you can restart. And then if it tries a new configuration or generates a new configuration and it is in that window where it could restart, it can recognize that the knobs that it's setting don't require a restart. Like, say there's some knobs that you could have tuned, but you didn't change it what it was before, and that's the only one that requires a restart. It knows that I don't have to restart, so it can apply the configuration and not just blindly bounce the system, right? Because that's trying to reduce the amount of interruption to the application from having the database offline. This sort of brings up another large point I want to bring up is there's a bunch of things that OtterTune could do to improve performance and efficiency, but we actually don't let it do these things. We actually have a deny list in the system to say don't tune certain knobs a certain way, other than just restarting. Like, you can turn off fsync in your log flushes when transactions commit, and that's going to make things run really fast because you're not flushing things out to disk. And OtterTune will learn very quickly. Their algorithms will learn very quickly that turning off disk writes make things go faster. Not surprisingly, but because it doesn't know, whether if the system crashes, whether your company or your organization can afford to lose the last 10 milliseconds of the log, and what are the external costs of that. It doesn't know what that is. So we actually put, tuning the knobs that way. It's something that could affect the correctness or the durability of data. We put that in the deny list. And you have to actually explicitly override it and say, okay, I'm aware of the consequences of tuning this a certain way, and let OtterTune do that for you. So we're very conservative in what OtterTune can touch, because again, certain things will improve performance, but could affect the quality of your data, the correctness of your data. All right, and then the last problem, again, we said that how long does it take to do the restart? Again, this is unfortunately ongoing research. We don't have a good answer to this. We think we're going to have to end up training another model that can predict my knobs are a certain way, and I set them to another way, and I have to restart, then try to predict how long this can take. But it can depend on many different factors. All right, so just to finish up here, what I've shown today is that, what I've argued is that how machine learning can be used to optimize and improve the performance of databases just by tuning the knobs.
Andy, your database is now optimized and ready to use.
I always forget that. Sorry. Okay, it's on the timer. So let's go back now to our tuning database, and I'll drag this over this here if I can. Nope. Sorry, 1 sec. All right, let me just duplicate screen. That's just easier. Sorry, do that. Okay, so let me go back to the dashboard and refresh this. All right, so we can go to our tuning days here, and we see that we've been tuning performance, and we can go look list of our configurations. There's no way to hide this. Sorry, that doesn't matter. We can look at a list of our configurations, and we can see what OtterTune has been modifying, and we can compare against the default config that we started with. And you can see here the changes that OtterTune has made for the knob that we want to tune. And then we go now into our performance charts, and we can see here over time how the performance has changed. And you can see that, again, we start off at the very beginning doing about 1,400 transactions a second, and it looks like our peak we got was 1,800 or maybe 1,900 here. So we want to compare against our monitoring database, again, where OtterTune is just collecting the data. It's not making any changes to the configuration, so we can include that in our plot. And you see here that it similarly started off around 1,200 transactions a second, and you can see how OtterTune is improving performance. So this is a short demo because this is only tuning for an hour. Could potentially let this run longer and see how OtterTune fares. But we're roughly getting around the 1,800 versus 1,500. maybe a 10 to 20, 12, 10% to 20% improvement here. Again, if we let it longer, if we had more time, we would see, OtterTune get better and better. Okay, so with that, I gotta break out of this, stop share. Let's open it up to questions. I'll share the screen again.
Thanks, Andy. We really appreciate that. It was awesome. Yeah, I'm actually kind of taking notes as we saw on the side here. Hey, we have a couple questions for you that came in the chat. We're going to start with a couple of these. Let's start off with this one. How do you ensure the robustness of the configuration that you recommended? I mean, are there any ways to you did a little bit of talk about this? I think they just want to make sure that are there any ways to guarantee that robustness to make sure that the system doesn't break down? You discussed that a little briefly. Do you want to just cover that again really quick?
So can they define what they mean by robustness? Like the quality of the configuration?
Well, I would say that that's the question we got, but I will take a look and see whether they can come back and ask for some more. So we'll wait for them to come back with some more. So
just to repeat the question. So the question is, how can we guarantee the robustness of the configurations?
Yes.
In some ways you can't, right? Because it's machine learning. It's how to say this? There's no guarantee that during the sort of discovery phase of when it's trying out, when it has no prior knowledge, you can't guarantee that like, oh, I'm immediately going to jump to the magical best solution. Because if that was the case, then you didn't need any of this machine learning stuff. So I think the way we're proceeding with this is that as we get more people using the OtterTune service, we see more databases, we see more different workloads, and that we use that to bolster our models so that in the future, when someone comes along with a database we've never seen before, but it looks very similar to a database we tuned the prior week, then it would take less time for us to generate a better configuration. All right, maybe that gets us the 80% of the benefit of what OtterTune could get right away. And then over time, as we sort of hone the models or customize it for exactly what your application is trying to do, then we can get even better performance. So the other guardrails that I talked about to make sure that OtterTune doesn't try random things that would put you in a bad state. Like, for example, the buffer pool size. MySQL, Postgres, every database system will let you set it to really small values. Like, you could set it to 10 megabytes. But we know as humans that that's stupid. That's not something we want to do. So when we do our sampling process, we're looking at deciles or quantiles of potential values where we know that it's in the right direction. Right. So an obvious thing is like when you first time you look at an RDS instance, if you're running with a default RDS configuration, you probably don't want to reduce the buffer pool size, right? You want to at least use that as a starting point and figure out how high you actually should put it.
Yep. Yep, that makes sense. And yep, thanks for answering that one. So the next question that came in was, are there any support right now for non-relational databases in your model? Do you do any knob tuning for any non-relationals?
So we get this question a lot. We've been asked mostly for Cassandra of all the NoSQL non-relational databases. Again, there's nothing in our machine learning algorithms that are specific to Postgres, MySQL, Oracle, or whatever database. It's all, again, the driver infrastructure. So, my background is in Postgres and MySQL. My PhD advisor embedded Postgres. I'm focused on that, and I think there's a larger install base for those systems. If someone's very interested in using OtterTune for a NoSQL system, by all means, let us know. Reach out to us, and we can see what we can do. But we just have not seen the demand for other, at the same level of Postgres and MySQL for other database systems.
Sure.
SQL Server is probably the next database we would probably choose. I can't guarantee that, but that's most of our, for the requests of the databases we don't currently support, SQL Server comes up next.
And thanks for that answer. And the next one that came in was, and I think this is something that maybe you could clarify again, was how does the initial configuration affect the tuning performance? Does your system provide a way to basically get out of a bad local initial configuration to basically get to a better tuning, or is it just a continuous process of optimization?
So the question is, if I have a really bad configuration, is that going to hamper me from getting to a much better configuration? Like if I'm at a really bad state, is that going to prevent me from getting to where I really should be? No, it could potentially mean it could take longer. It depends. There's other factors involved in it. Like if your workload is very random, like it's the number of queries you're executing during the day just varies all the time. That can take a long time to figure out what's going on. If you have like a binaural pattern where there's more queries during the day, less queries at night, and that's very cyclic, we can constrain the tuning window to look at that period. I haven't seen the case. Yeah, it's a good question. I don't think it should be a problem. We haven't seen one where somebody has like a terrible configuration. I mean, we've done deployments where we start off with the default Ubuntu configuration, and what happens is in the very beginning, if you don't have any training data, you do the sampling period for the first 10 iterations. It's called Latin hypercube sampling. It's not a technique we invented. It's a standard approach to machine learning. But that's where you're looking at random values in different sort of bucket ranges, and that'll allow you to break out of that terrible configuration pretty quickly.
Okay, great. So the next question comes around about something called the Autonomous Database by Oracle. Have you heard about it? Yeah.
Every time we get asked this every time. Yes.
You got it. Okay, great.
Yes. Do you want me to just pontificate about it? Is that question or like?
I think you want. I think they were just asking for pros and cons and versus that. Great. So
okay. So
yeah.
I know that people working on the Oracle's autonomous database stuff, I think very highly of them. They're taking a sort of somewhat a white box approach, like they're modifying the internals of the database system to introduce some of their tuning tuning capabilities. Some of it has been enhanced, but a lot of it is actually running the same sort of methods and algorithms that they developed in the 2000s, sort of with these sort of GUI tools or like local tools we would run that DBAs would run that would make recommendations to make changes. So a lot of that still is based on that sort of prior technology. They've enhanced a bunch of it with machine learning, reinforcement learning, which I think is good. Oracle's thing is doing a lot more, right? They're doing index tuning, they're doing partitioning, they're doing security patches, they're doing a whole bunch of things. OtterTune is currently only focused on knob tuning because we think that's and we can work in other data systems, whereas Oracle's stuff is only going to work at Oracle. Right. Oracle also has their MySQL HeatWave. They just announced their autopilot feature a few weeks ago. That is not doing knob tuning, and the tuning components that they provide, they're all recommendation tools, meaning they don't actually apply the changes automatically. A human has to come and say yes, 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 and click yes, and make things happen. Microsoft has a bunch of the stuff in the space. They were at the forefront of automated database tuning in the 2000s with the Auto Admin project. Some of that stuff is showing up in SQL Server Azure, so they can do index tuning. All that stuff I think is great. There isn't going to be anybody trying to make an autonomous version of Postgres, at least not in the short term, right? It's just too many moving parts.
Right, that makes sense. So, and the next question actually is a really interesting one. About in real time, can you integrate OtterTune with a database optimizer so that it could change the configurations in real time for workload changes?
So the question, like the optimizer for query planning.
Yeah, I think that's what they're looking for is query planning, because they're looking for. I think they're asking if you can, like how you would work in kind of a real time workload if there were suddenly major changes in workload or shifts in workload. Would OtterTune be able to catch those and help optimize for that as well?
Yeah. So we don't have anything public about this. We've been working on doing workload shift detection, and we actually think we can use sort of the same models that we have to do prediction of like how much better we think the system will be based on a new configuration. You can sort of use the same models to recognize that, hey, we thought we were running with the best configuration because the workload used to look like this, but now something has changed, something has shifted, and therefore we should retune things. That currently does not exist in the commercial version. Yeah, so it could be done for this. For stuff with the query optimizer actually isn't going to make a difference. There are some knobs you can tune that would, at least in Postgres, you can change the cost estimations or ratios of cost estimates sequential scans versus index scans, and tweaking those can actually help. But to do this in real time, you wouldn't actually use the optimizer. You basically want to use the same infrastructure we have now, where we're observing the workload, we're observing these metrics, and use that to trigger then, hey, something has changed. Let me go ahead and apply new configuration. Then what we want to be able to do, what we currently can't do, is provide a human explainable or human explanation or human readable explanation of why things have changed or why your workload did a certain thing or why we tuned these things a certain way. Like we want to be able to do is like, if we detect one of these workload shifts and say, hey, yesterday your workload was very read heavy, but now it looks like it's more write heavy. That's why OtterTune changed these knobs. I think that's what people would want, and we're just not there yet. But this is something we're interested in doing.
Okay, I think we have time for one more question, so I'm going to pull one off the end of the list. One of the persons has asked if you can give a little bit more differentiation on the difference between your configuration changes and potential environmental changes. Right? Does your system detect environmental changes, and if so, how does that work? But I mean, they're just wondering like if you can clear up the difference between the two.
Yeah. So this is so they're basically asking like, if my hardware changes a certain way, like the disk gets slower because of degradation problems. If I'm running in a VM and somebody else is in a VM on the same box as me and they're like doing Bitcoin mining and it slows me down, how do I handle that? This is part of the reason why we're focusing on RDS, because that at least gives us a stable environment in terms of like, it gives us an environment where the hardware is standardized, meaning we don't have to worry about sort of arbitrary SSDs or off-brand RAM people are using, right? If you're running on-prem, and so we're not there yet. We think we can use again the same models to sort of recognize that you're on a box that has this instance size of this amount of provision IOPS. You should be getting roughly this performance, but we identify that you're not getting that, and so we could maybe alert you to say, hey, you're not getting the best performance in the current instance size you're at. Maybe you want to transition to something else. It's sort of related to capacity planning. Can I figure out like what performance I should be getting, or would I be getting if I downsize or upgrade? So this is a very, very hard problem. We don't have an answer to it just yet. I think that the next step, actually, I will say, RDS is actually pretty good in terms of like, you seem to be isolated from your neighbors. We have not seen sort of wild swings in performance. I know people have reported like 20% differences, but so far we haven't really seen it. I'm sure it happens, but I just don't know yet. But I think the first problem we're trying to solve is actually capacity planning. To use our same models to say, you're running on this instance size, this amount of provision IOPS, you're paying Amazon this much. If you downgrade or upgrade or tweak your provision IOPS, you'll get this performance, and then we can guide them to see whether they want to make that change. I think that's sort of the first approach that we can do, assuming that the hardware environment is stable. And then once we have that working, we can then use that as like a watchdog to see whether things have changed enough, or you're not getting the performance you should be getting.